Sixth grade, happy science. We're going to work through a little bit of an experiment and then the math and science. The math and science talks about sonar and how we use them to find fish as we bounce off waves. So we ended the chapter the same way we started that chapter when you were making your predictions on looking at the different depths of ocean, how long it took. So today I'm going to tell you how we locate earthquakes with that. So it says at the top here, guys, it says earthquakes produce several kinds of waves that travel through Earth. P waves are the fastest, with an average speed of going 6 kilometers a second. S waves are slower. So P stands for primary, guys, first, S secondary. They're slower with an average speed of 4 kilometers a second. Stations record the strength of the waves and when they arrive. By noting the difference in the time between the arrival of the P and the S waves, scientists can calculate how far away the center of the earthquake lies. So we're going to see how they do that. It says, suppose that P waves start at 9:29 and S waves start arriving at 9:35. How much longer did it take the S waves to travel from the earthquake center to the station? So guys, you're just going to take 9:35 and subtract 9:29 from it. So I'm just going to do that on a different sheet here. So I got 9:35 minus 9:39 becomes a 2:15.600. It's going to take 6 minutes. So I'm back to this one. Number one, 6 minutes. Number 2 says, find out where on the graph the S and the P wave line are 6 minutes apart. Use a scrap of paper and the y-axis to mark off the line measuring 6 minutes. Slide the paper up the curve of the P and the S lines until it fits the thing. So what they do, guys, is you stick a piece of paper here and you measure from here to here on your piece of paper. Then you take this gap and you start sliding it up the paper until you have the same distance apart. So obviously this is too small here, too small here. If we kept these lines going, it'd be really big line here. So see this distance? It goes to about right here. Now what we do is we take that line straight down and boom, you have it run into what looks like the 5 there. So 3 says, how far away is the earthquake center from this station? It is 500. I lied. It is 5,000 because I have to erase that so I can see it. It is 1,000 per thing. So I ran into the 5 there. It's 5,000 kilometers. Number 4 says, can scientists decide where the earthquake occurred using just that information? Well, let's do that. So, guys, here's another screen here. And you can tell that's United States, right? So here's the station right now. This station just recorded the information we talked about, and I knew the earthquake occurred 5,000 miles away from it, 5,000 kilometers. So if I go out 5,000 kilometers and then draw a circle, that earthquake could have occurred anywhere on that line. So number 4, can scientists decide where the earthquake occurred using just this information? The answer is no, because it could occur anywhere on this circle. Okay, now I have a second station right here that recorded the information. It too creates a circle, and its circle looks like this. Now, guys, with 2 stations, I know the earthquake either occurred here or the earthquake occurred here. Even with 2 stations, it's not enough. So now I take a third station like this, and I take its measurement, and its big circle cruises through here and goes way around like that and create a big circle. And so now I know this is the earthquake. So at the top of your page, guys, when you want extra credit, you write number 4 takes 4 stations. I lied, takes 3 stations. So up here I'm writing number 4 takes 3 stations to be able to get a measurement. Okay, guys, coming up next is the experiment for the convection current that was found on the previous page. When you get done with that, watching that experiment, there is going to be a video at the end that tells you what color is on the bottom. You write that for extra credit too, color on bottom. So watch the video. It'll show you what color's on the bottom, and then you write that on there. Have a great day. All right, 6th grade, we're going to try a little bit of an experiment here. Following along on that page there, we're going to add 4 drops of red food coloring on the left, close to the side, let it drip down the side, not from high. There we go. Here goes in 4 drops of red food coloring, say a little prayer. All right, good enough. Now we're gonna head to the other side and we're gonna add the green drops of food coloring. So on the left side here, guys, it's sitting on cups of hot water. Sorry, and on the right side, it's sitting on cups of cold water. And we're gonna hopefully see if we can tell the difference between the way the food coloring spreads out over time based on hot and cold water. Now you're starting to understand why we don't do science experiments too much, because it's kind of boring. Maybe I'll put a red drop on the over by that other cup. Ooh. Now, if you were asking me, I would think it would be the other way around. I would think the red would spread out more than the green, because I would think red, hot, moves faster. But it kind of looks like green, cold is moving faster. But man, is this super interesting. So we're supposed to stare at this screen for 3 minutes. We are currently 1 minute into this. And you're starting to get an idea of what's happening. This is kind of giving you an idea of what's supposed to be going on inside the Earth with convection currents, where the difference in temperature causes things to move differently. So whether we got it going the right way with the food coloring, the good news is you can see it moving, even though obviously my little Tupperware bin here is not moving at all. So the particles of water, because of the different temperatures, are moving around. That's colliding with the food coloring in there, and it's slowly spreading around. And in fact, you can see how they're kind of going straight across the bottom there as the green and the reds are starting to mix into each other. And so over time, you can see how the water is going to come to what we call equilibrium, where it becomes the same temperature. What is kind of interesting is here on the right side, you can see how the green is kind of forming that big, huge, solid blob back there. So you can see how the edge of that Tupperware, where it's really cold over here on the left-hand side, is forming that ring where it's sunk to the bottom and sitting there. The red obviously is kind of just sunk to the bottom because it's obviously denser to get there. So I didn't really have good food coloring. I had stuff that's supposed to be made for cakes. So you mix it in with a frosting to change the frosting a different color. So I think that's part of the problem with it. I didn't have the right food coloring, but you can see how it's slowly moving out here, guys, and will eventually all mix together. You can decide if you think it should have been faster or a different color. I think if we'd have done it perfect and had the right stuff, I think red mixes faster than green, but it's kind of interesting how it looks. All right, thanks for watching a science experiment. Feel free to do it at home if you want to try it yourself. Guys, I'm going to give you a little side shot of this experiment a little bit. If you look from the side here, okay, I'm going to go back up to the top. If I move my finger right, sorry. You can see how it all looks like it's kind of moving together with the red and the green there. If you can kind of come down by the side here, you can see the red is way more on the top and the green is sitting on the bottom, which goes along with what we talk about. Hot rises, green sets to the bottom. So if I look at the bottom down here, you can see how the green's along the bottom and the red is more on the top. So I think we're doing it right. The hot is rising and the cold green is sinking.